chemotherapy drug can reach the bloodstream, but can it reach the center of a tumor where the pressure is highest? That question is what this work is built around, predicting the stress and interstitial fluid pressures hidden inside a tumor using ultrasound strain elastography and a three-dimensional biphasic biomechanical model. As cancer cells proliferate, the tumor grows and the surrounding tissue pushes back against that growth. This creates compressive stress. At the same time, fluid moving through the tissue generates interstitial fluid pressure. These mechanical effects are directly linked to tumor invasion, metastasis, and the ability of the drug to penetrate to the tumor. Most previous studies focused on tissue deformation or fluid pressure separately. In our work, we combined both in a single model that predicts tumor stress and interstitial fluid pressure simultaneously. From an engineering perspective, the tissue interstitium is modeled as a porous biphasic medium consisting of a solid matrix and a fluid phase. The solid phase represents the tissue structure, while the fluid phase moves through the interstitial space. To describe the system, our model is based on four fundamental principles: balance of mass, balance of momentum, material behavior, and compatibility conditions. The momentum equation couples tissue deformation with the pressure gradient, while the fluid equation follows Darcy type flow through the porous tissue. We also model the fluid leakage from blood capillaries into the interstitial space and the drainage toward lymphatic vessels, which represents the physical source of the pressure distribution inside the tumor. To make a model practical rather than purely theoretical, we developed a user interface application that allows healthcare personnel to enter tissue and tumor parameters and obtain estimates of stress and interstitial fluid pressure automatically. Now, let us look at the results. For an elliptical tumor at 10 minutes, the model predicted a maximum displacement of approximately 1.39 mm for benign tissue and 1.28 mm for malignant tissue. This means that the malignant tissue accepts less deformation under the same applied load, indicating a stiffer mechanical response. The most important results appears in the interstitial fluid pressure maps. The predicted IFB is high and nearly uniform at the tumor center, and it's gradually decreased toward the periphery. This pattern is consistent with the experimentally reported observation in this literature. In engineering terms, the tumor doesn't have a uniform internal pressure environment. The central region experiences elevated pressure, while the peripheral region experiences lower pressure. As a result, the pressure gradient that would normally assist in word transport becomes significantly reduced at the tumor core. The stress maps provide another perspective by visualizing how mechanical stress is concentrated around the tumor and distributed through the surrounding tissue. Clinically, this model could help physicians better understand the pressure environment inside a tumor, which may support future treatment planning and the assessment of drug delivery challenges. Our goal is not only to image a tumor, it's to quantify its hidden mechanical environment by combining strain elastography with a three-dimensional biphasic biomechanical model. This work takes a step toward making a tumor stress and interstitial fluid pressure measurable from outside the body, because the real barrier to treatment is not always biological, sometimes it is mechanical, and now we can finally measure it.